Welcome to a journey into one of the most dramatic transformations occurring on our planet today. In the vast white expanse of the Arctic, Greenland's massive ice sheet, the second largest on Earth, is melting at unprecedented rates. This isn't just a local phenomenon, it's a global crisis with far-reaching consequences that will reshape our world for generations to come. Today, we'll explore the alarming acceleration of ice loss, the science behind it, and what it means for coastal communities, ocean currents, and life as we know it. Join me as we examine the evidence, understand the implications, and confront the reality of what's happening in Earth's frozen north. The numbers are staggering. Satellite data from the European Space Agency's Cryo-SAT-2 and NASA's ISAT-2 missions reveals that Greenland is now losing approximately 300 billion tons of ice annually. To put this in perspective, that's a six-fold increase compared to the 1990s, when the rate was around 50 billion tons per year. This acceleration has been particularly pronounced in the last decade, with several record-breaking melt seasons since 2012. The northeast and northwest regions of Greenland, once considered relatively stable, are now showing the most dramatic losses. What's driving this rapid change? Scientists point to a combination of factors. Warmer ocean temperatures are undercutting coastal glaciers, summer melt seasons are getting longer, and as ice melts, it exposes darker surfaces that absorb more solar radiation, creating a dangerous feedback loop that accelerates melting even further. The summer of 2019 marked a particularly alarming milestone in Greenland's transformation. Unusually warm air masses settled over the ice sheet, triggering surface melting across an astonishing 90% of its area. On a single day, July 31, 2019, Greenland lost approximately 12.5 billion tons of ice. That's enough water to cover the entire state of Florida in nearly 5 inches of water, released in just 24 hours. These extreme melt events were once considered rare anomalies, but they're becoming increasingly common as our climate warms. Scientists monitoring the ice sheet have observed that its fundamental equilibrium has shifted. Historically, winter snowfall would replenish the ice lost during summer months, maintaining a relative balance. But since the 1990s, this equilibrium has been disrupted. Summer melting now consistently outpaces winter accumulation. Even in years with above-average snowfall, the ice sheet continues to lose mass. This suggests that a critical threshold has been crossed. Greenland's ice is now in a state of persistent decline. Greenland's ice sheet contains enough water to raise global sea levels by approximately 24 feet, or 7.4 meters, if it were to melt completely. While a total melt isn't expected in the near term, the current rate of ice loss is already contributing about 0.8 millimeters to sea level rise each year. This may sound insignificant, but it compounds over time and combines with other sources of sea level rise, including thermal expansion of ocean water and ice loss from Antarctica. The effects are already visible in coastal communities worldwide. Tidal flooding has increased by 50% in many U.S. coastal cities over just the past 2 decades. Looking ahead, projections suggest that by 2050, sea levels could rise by 15 to 30 centimeters, that's 6 to 12 inches, above 2000 levels, with Greenland's contribution making up a significant portion of this increase. The economic implications are substantial and growing. According to a World Bank report, without adaptation measures, annual damages from coastal flooding could reach 1.8% of global GDP by 2080. Infrastructure worth trillions of dollars is at risk, from major cities like Miami, Shanghai, and Jakarta to critical ports, power plants, and transportation networks. For island nations in the Pacific and Caribbean, the threat posed by Greenland's melting ice isn't just about economic damage, it's existential. These low-lying countries face the prospect of partial or complete submersion as sea levels continue to rise. Communities that have existed for generations may be forced to relocate entirely, potentially creating millions of climate refugees in the coming decades. What makes Greenland's contribution to this crisis particularly concerning is its non-linear nature. Recent research published in Nature Climate Change suggests that certain glaciers may reach tipping points where retreat becomes self-sustaining and irreversible on human timescales. This means that even if global temperatures were to stabilize, some ice loss processes might continue regardless, committed to a path of continued melt. For communities on the front lines, this creates an urgent need for both mitigation and adaptation strategies. Some island nations are already investing in seawalls and elevated infrastructure, while others are developing contingency plans for potential relocation of their populations, a devastating prospect for cultures deeply tied to their ancestral lands. Beyond rising seas, Greenland's melting ice is triggering another profound change that could affect climate patterns worldwide. The massive influx of freshwater into the North Atlantic is beginning to alter ocean circulation patterns, particularly the Atlantic Meridional Overturning Circulation, or AMOCR, which includes the Gulf Stream. Recent measurements indicate the AMOC has slowed by approximately 15% since the mid-20th century. This isn't just an oceanographic curiosity, it's a fundamental shift in how our planet distributes heat. The Gulf Stream delivers substantial warmth to Western Europe, moderating its climate. A significant slowdown could lead to cooler temperatures in parts of Europe, even as global average temperatures continue to rise. This creates a paradoxical situation where Greenland's melting may temporarily mask some effects of global warming in specific regions, potentially creating a false impression that climate change is less severe than it actually is. The freshwater entering the ocean also carries with it sediments and nutrients that have been locked in ice for thousands of years. These materials alter marine chemistry and biological productivity, with consequences for carbon sequestration and fisheries that scientists are only beginning to understand. The oceanographic shifts triggered by Greenland's melting ice are already affecting marine ecosystems. Researchers have detected changes in fish migration patterns and plankton distribution that correlate directly with these changes in temperature and salinity. Commercial fisheries in the North Atlantic may face significant challenges as traditional fishing grounds become less productive or experience shifts in species composition. Cold water species are moving northward as waters warm, while the influx of nutrients from melting ice is altering the base of the marine food web. Some areas are experiencing algal blooms, while others see declining productivity. These changes ripple through the entire ecosystem, affecting everything from microscopic plankton to large marine mammals. For coastal communities that depend on fishing for their livelihoods and food security, these shifts represent yet another dimension of the challenge posed by Greenland's transformation. Indigenous communities in the Arctic, who have relied on predictable sea ice conditions and marine resources for thousands of years, are particularly vulnerable to these rapid changes. Their traditional knowledge, passed down through generations, is becoming less reliable as conditions change faster than at any point in their cultural memory. The precision with which scientists can now measure ice loss has improved dramatically in recent years, giving us unprecedented insight into what's happening in Greenland. The graceful satellites, that stands for Gravity Recovery and Climate Experiment Follow-On, can detect minute changes in Earth's gravitational field caused by mass movement. This allows researchers to calculate ice loss with remarkable accuracy, even in remote and inaccessible regions. Additionally, a network of GPS stations installed directly on Greenland's bedrock measures how the land rises as ice weight is removed, a phenomenon called isostatic rebound. These measurements provide independent confirmation of the scale and rate of ice loss. Emerging technologies are further enhancing our understanding. Autonomous underwater vehicles now explore the complex interface where glaciers meet the ocean, revealing interactions previously hidden from view. Machine learning algorithms are improving ice sheet models by identifying subtle patterns in satellite data that human analysts might miss. These technological advances are crucial for refining projections and developing effective adaptation strategies. They allow us to monitor changes in near real time and provide early warnings of potential tipping points or acceleration in ice loss. Using these advanced monitoring systems, climate models project a concerning future for Greenland's ice. Under current emission scenarios, Greenland could lose between 8 to 11% of its total ice mass by 2100. This would contribute significantly to global sea level rise and potentially trigger irreversible changes in ocean circulation. Even more alarming is the long-term outlook. Even if global temperatures are stabilized at 1.5 degrees Celsius above pre-industrial levels, the ambitious goal of the Paris Agreement, Greenland is still expected to continue losing ice for centuries. This is due to the thermal inertia in the climate system and self-reinforcing feedback mechanisms already in motion. Some of these processes, once started, cannot be easily reversed. The darker exposed surfaces absorb more heat, warming continues at depth in the ice sheet, and as glaciers retreat into deeper basins, they become more vulnerable to warm water intrusion. These projections underscore the urgency of both mitigation efforts to reduce greenhouse gas emissions and adaptation strategies to prepare for the changes that are now inevitable. They also highlight the importance of continued monitoring and research to refine our understanding of these complex processes. The transformation of Greenland's ice sheet represents one of the most visible manifestations of climate change on our planet. Its accelerating melt serves as both a harbinger of future challenges and an urgent call to action. The data presents a clear warning. What happens in Greenland will not stay in Greenland. The consequences of this massive ice loss will be felt globally for generations to come. While the situation is concerning, it also underscores the importance of both mitigation and adaptation efforts. Reducing greenhouse gas emissions remains the most effective way to limit long-term ice loss. Every fraction of a degree matters. The difference between 1.5 degrees Celsius and 2 degrees Celsius of warming could mean meters of additional sea level rise over the coming centuries. Meanwhile, coastal communities must simultaneously prepare for the reality of rising seas through infrastructure adaptations, managed retreat from the most vulnerable areas, and development of new approaches to living with water. The monitoring systems now in place provide valuable early warnings, allowing society time to respond if we choose to heed these signals from Earth's frozen north. As we've explored throughout this journey, Greenland's melting ice sheet represents far more than a distant environmental change. It's a planetary transformation with implications for every continent and coastline. The six-fold increase in ice loss since the 1990s, now reaching 300 billion tons annually, is rewriting our future. From the rising seas threatening coastal cities and island nations to the disruption of ocean currents that regulate our climate, the consequences are far-reaching and increasingly visible. The science is clear. Even with immediate action to reduce emissions, some degree of continued ice loss and sea level rise is now inevitable due to processes already set in motion. Yet the rate and ultimate extent of this change remain within our influence. The sophisticated monitoring systems tracking these changes offer us both warning and opportunity, the chance to adapt our coastal communities, rethink our relationship with rising waters, and perhaps most importantly, to mitigate the worst potential outcomes through decisive climate action. Greenland's ice sheet, which has remained relatively stable for thousands of years, is now a dynamic system in rapid transition. Its message to humanity is unambiguous. The stable climate that enabled the development of our civilization is changing, and our response in the coming decades will determine the world future generations inherit. The transformation of Greenland is not just a scientific measurement, it's a call to reimagine our relationship with the planet's systems upon which all life depends. Thanks for watching. Please like, subscribe, and hit the bell icon for updates. Your feedback is appreciated. We hope to see you again.